Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video that you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present Novolac Epoxy Resins. Novolaks are produced by reacting phenol with methanol formaldehyde. Novolaks, sometimes written by SC, like Novolacs, are low molecular weight polymers derived from phenols and formaldehydes. The term comes from a Swedish word lac for lacquer and Latin novo for new. Since these materials were envisioned to replace natural lacquers such as copal resins, copal is a tree resins, particularly the aromatic resin from the copal tree. Europeans found it to be a valuable ingredient in making a good wood varnish. It becomes widely used in the manufacture of furniture and carriages. Therefore, Novolac comes to substitute this material. Phenolic resins were discovered by Bayer in 1872 through acid-catalyzed reactions of phenols in acetaldehyde. Kleberg found in 1891 that resinous products could also be formed by reacting phenol with formaldehyde, but it was Backland who was granted patents in 1909 describing both base-catalyzed results known as bakelite resins and acid-catalyzed Novolac products. Typically, Novolaks are prepared by the condensation of phenol or a mixture of para and meta-cresols with formaldehyde as formalin. The reaction is acid-catalyzed. Oxalic acid is often used because it can be subsequently removed by thermal decomposition. Novolac have a degree of polymerization of approximately 20 to 14. The branching density determined by the processing conditions M versus para-cresol ratio as well as CH2 to cresol ratio is typically around 15%. In the synthesis, phenol reacts with formaldehyde to form ortho or para-hydroxy methylphenols, which in further reactions with phenols form a linear polymer called Novolac. Another term for Novolac is phenol formaldehyde resins, also called phenolic resins or phenol plasts. Phenol plasts were the first commercial synthetic resins. They have been widely used for the production of molded products including billiard balls, laboratory countertops, and coatings and adhesives. They were at one time the primary material used for the production of circuit boards, but have been largely replaced with other epoxy resins and fiberglass cloth. Phenol formaldehyde resins as a group are formed by a step-growth polymerization reaction that can be either acid or base catalyst. Since formaldehyde exists predominantly in solution as a dynamic equilibrium of methylene glycol oligomers, the concentration of the reactive form of the formaldehyde depends on temperature and pH. Therefore, Novolaks are phenol formaldehyde resins with a formaldehyde to phenol molar ratio of less than 1. In place of phenol itself, they are often produced from cresols, methylphenols. The polymerization is brought to completion using acid catalysis such as sulfuric acid, oxalic acid, hydrochloric acid, and rarely sulfonic acid. The phenolic units are mainly linked by methylene and or ether groups. The molecular weights are in low thousands, corresponding to about 10 to 20 phenol units. Obtained polymer is thermoplastic and require a curing agent or hardener to form a thermoset. Hexamethylene tetramine is a hardener added to crosslink Novolac. At a temperature greater than 90 centigrade, it forms methylene and dimethylene amino bridges. Results can also be used as a curing agent for Novolac resins. In either case, the curing agent is a source of formaldehyde which provides bridges between Novolac chains, eventually completely cross-linking the system. Novolacs have multiple uses as tire tackifier, high-temperature resin, binders for carbon-bonded refractories, carbon brakes, photoresists, and as a curing agent for epoxy resins. Novolacs are especially important in microelectronics where they are used as photoresist materials. They are also used as tackifiers in rubber. Epoxy Novolacs are some of the most advanced epoxies available, offering benefits such as easy application, less odor, low permeability, and more. Depending on the specific formulation, epoxy Novolac either require heat to fully cure or can cure at room temperature. This type of epoxy is commonly used for applications requiring high level of corrosion, temperature, and chemical resistance. Epoxy Novolacs are valued for their excellent resistance to damage when exposed to commercial and industrial strain acids and other chemicals. They can also handle the higher temperature levels without degrading or losing their positive characteristics. The reaction of epichlorohydrin and Novolacs produces Novolacs with glycidyl residues such as Epoxyphenol Novolac (EPN) or Epoxycresol Novolac (ECN). These highly viscous to solid resins typically carry 2 to 6 epoxy groups per molecule. By curing highly cross-linked polymers with high temperature and chemical resistance but low mechanical flexibility are formed due to the high functionality and hence high cross-link density of these resins. Epoxyphenol Novolac resins are produced in the presence of sodium hydroxide NaOH. The hydroxide ions OH- remove the proton H+ from the phenyl hydroxyl ROH group to create nucleophilic phenyl hydroxide. The hydroxide substitutes the chloride in epichlorohydrin, which links the phenolic units with the epoxide. Both the Novolac resins and epoxide groups may be modified with other functional groups to alter the properties of EPN. The choice of EPN resins may be determined by the particular advantage of the selected formula. Some resins are easier to apply and dry faster. Others have extra high resistance properties. Others retain their properties along a large temperature range. The best EPN product depends on the application needs and environment. Epoxycresol Novolac epoxy resins are used widely as electronic encapsulating materials. ECN Epoxycresol Novolac resin is synthesized from paraformaldehyde and Epoxycresol in the presence of a mixed catalyst, oxalic acid, and another co-catalyst. Then the resultant resin is further reacted with epichlorohydrin to prepare Epoxycresol Novolac epoxy resins. Phenolic resins are ideal for in structural adhesives and composites since they are flame retardant and cost effective. The major drawback thus far for typical phenolic networks, including both phenolic Novolacs cured with hexamethylene tetramine (HMTA), has been their brittle nature, originating from high crosslink densities and high void contents. Volatilities such as water and ammonia released during the cure reaction cause the network to have high void contents. Epoxyphenol Novolac resins (EPNs) are liquid or semi-solid reaction products of epichlorohydrin and phenyl formaldehyde Novolacs. These resins combine the high thermal stability of Novolacs with the high reactivity of epoxy resins. They are known for their outstanding dimensional stability, high resistance to creep at elevated temperatures, favorable price to performance characteristics, and high chemical resistance including many acid, bases, and solvents. It is mentioned that an epoxyphenol Novolac EPN is an epoxy resin where the epoxide functional group is attached to the phenolic oxygen of a phenolic Novolac. As such, each phenol oxygen of the Novolac resin is attached to an epoxide ring. A single EPN polymer contains many epoxide groups, making the molecule multifunctional. When cured to make an epoxy coating or adhesives, the multifunctionality allows for a high degree of cross-linking, leading to high resistance. The most common precursors to phenolic resins is phenol. More than 95% of phenol is produced via the Kuhlmann process developed by Hock and Lang. Kuhlmann is obtained from the reaction of propylene and benzene through acid-catalyzed alkylation. A small amount of phenol is also derived from coal, formaldehyde produced by the dehydrogenation of methanol. It is used almost exclusively in the synthesis of phenolic resins. Iron oxide, molybdenum oxide, or silver catalyst are typically used for preparing formaldehyde. Epoxyphenol Novolac resins are produced by the reaction of phenol Novolac with epichlorohydrin in the presence of sodium hydroxide NaOH. The hydroxide ions remove the proton from the phenyl hydroxyl group to create a nucleophilic phenyl hydroxide. The latter hydroxide substitutes the chloride in the epichlorohydrin, which links the phenolic units with the epoxide. Both the Novolac resins and epoxide group may be modified with other functional groups to alter the properties of EPN. The family of EPN resins have various properties, but the common ones could be viscosity at 52 centigrade between 600 to 50,000 centipoise, epoxide equivalent weight EW between 160 to 270 gram per equivalent, functionality 2.2 to 3.8, color 1 to 3 Gardner color scale. Some EPN products in the market include Aditya Birla Group, Epotec YDPN, Miller Stephenson, Epon SU8, DuPont DEN 42 or 3X, for example 424, and Huntsman Epalloy. Regarding the largest manufacturers of epoxy phenol Novolac, we can name Huntsman, Olin, Hexion, Nanya Plastics, Kukdo Changchun Group, Sangmu Group, Aditya Birla Group, DIC, and Shengquan. Epoxyphenol Novolac resins are used in a variety of products including high-temperature structural adhesives, electrical laminates, high-performance composites, and molded parts. In industrial settings, EPN resins are used for the epoxy coating of tanks, pipes, floors, automotive parts, electronic parts, corrosion-resistant marine and industrial coatings, automotive primers, and coil and appliances coating, etc. The high chemical solvent and temperature resistance of EPN are especially useful for high-performance application and corrosion resistance. They are sometimes blended with other resins and or with fast-curing hardeners to avoid post-cure and to modify their properties. Due to their low flammability, outstanding dimensional stability, and slow heat release, they are often part of structural solutions for the aerospace and transportation industry. The choice of EPN resins may be determined by the particular advantages of a selected formula. Some resins are easier to apply and dry faster. Others have extra high resistance properties. Others retain their properties along a large temperature range. The best EPN product depends on the application's need and the environment. On the downside, epoxy Novolac resins can be brittle, are not color stable, and can be difficult to process due to their relatively high viscosities. For this reason, some grades are solvent cut or emulsified. waterborne. The top 5 companies hold a share of about 70% of the production. China is the largest market with a share about 24%, followed by Europe and North America, and a share about 23% and 22% respectively. Growing demand for adhesives, protective coatings, and composite materials around the world has had direct impact on the growth of Epoxyphenol Novolac. In terms of application, the largest application is composite materials, followed by adhesives. Epoxyphenol Novolac available in the market can be pure Epoxyphenol Novolac or Epoxyphenol Novolac solutions. ECN in a nutshell. To understand Epoxycresol Novolac or ECN, first we have to introduce a class of chemicals called cresols. Cresols, also known as hydroxytoluene, toluenol, benzol, or cressylic acid, are a group of aromatic organic compounds. These phenols or phenolics may be either natural or manufactured. They are also categorized as metal phenols. Cresols commonly occur as either solids or liquid because their melting points are generally close to room temperature. In its chemical structure, a molecule of cresols has a methyl group substituted onto the ring of phenol. There are 3 forms, isomers of cresols: orthocresols, O-cresol, metacresols, M-cresols, and paracresols, P-cresols. These forms occur separately or as a mixture, which can also be called cresols. Cresol Novolac epoxy networks exhibited improved processability under melt conditions relative to phenolic Novolac epoxy materials, and this was attributed to the presence of a methyl group adjacent to the hydroxyl group on the cresol's repeating unit, which reduced the rate of reaction between phenol and epoxy. Cresol Novolac Epoxy Resin is a type of thermosetting resin used in various applications such as adhesives, coatings, and composite due to its excellent heat resistance and chemical resistance. The Cresol Novolac Epoxy Resin market applications include EMC, electromagnetic compatibility, CCL, copper clad laminate, electronic ink, heat-resistant laminate composites, high-temperature adhesives, and others. EMC is used to prevent electromagnetic interfaces in electronic devices, while CCL provides insulation for printed circuit boards. Electronic ink is used in printing technology, while heat-resistant laminate composites are used in aerospace and automotive industries. High-temperature adhesive is used in industrial applications where extreme heat and pressures are present. Overall, Cresol Novolac epoxy resin has a wide range of applications due to its high strain and durabilities. Olin Corporation, Nanya Plastic, Hexion, DIC, Sinopec, Shengquan, and Changchun Plastics are some of the leading companies in the Cresol Novolac epoxy resin market. Olin Corporation is the market leader in the global epoxy market. Nanya Plastic, Hexion, and DIC are also among the key players in the market. Sinopec, Shengquan, and Changchun Plastics are emerging players in the market and are expected to contribute to the growth of the Cresol Novolac epoxy resins market. The USA is projected to hold the largest share in the Cresol Novolac epoxy resin market globally, followed by China. These 2 regions are expected to witness significant growth in the construction and electronics industries, which will drive to the demand for epoxy resin-based products. The method of reducing orthocresol Novolac epoxy resins involve polycondensation of orthocresol and formaldehyde in an equimolar ratio while heating in the presence of an acid catalyst in the medium of N-butanol. It continues with the reaction of the obtained product with excess epichlorohydrin while heating in the presence of an alkaline catalyst and afterwards distillation of epichlorohydrin and extracting the end product. Formaldehyde is used in the form of paraformaldehyde, and polycondensation of orthocresols and paraformaldehyde is carried out at 115 centigrade, first in the presence of oxalic acid until achieving 35 to 45 conversion, and then in the presence of toluene sulfonic acid. After the extraction of water and distillation at 65 centigrade, epichlorohydrin is added and then crushed sodium hydroxide is added. Finally, after the distillation of the excess epichlorohydrin and N-butanol, the resin is washed with chloroform and water and it is purified. Cresol Novolak are high heat resistance multifunctional epoxy resins. They're used for semiconductor encapsulants, electrical laminates, and solder resist. ECN is used as adhesives, coatings, and laminated material for applications that have a special requirement for heat resistance, anti-corrosion, and insulation. In general, the viscosities of ortho and paracresol Novolacs with similar molecular weights were almost identical, but were significantly lower than phenol-based oligomers. Comparatively, the phenol formaldehyde resin possessed the highest thermal and thermal oxidative stability, followed by metacresol formaldehyde resin. The paracresol formaldehyde has shown the least stability. In general, O-cresol Novolac epoxy resin market is segmented to low viscosity epoxy resins, medium viscosity epoxy resins, and high viscosity epoxy resins. Generally speaking, the performance of Novolac epoxy resin is much better than the performance of unmodified Bisphenol A epoxy resins. For comparison, in the adhesion terms, both resins perform excellently. Both resins are kind of weak in terms of UV protection. For VOC category, Novolac epoxy systems have no volatile content in terms of crystallization. Novolacs are much better. Novolac epoxy resins perform excellently in terms of moisture resistance and chemical resistance. A list of chemicals used for this comparison can be seen here. Some of the unique advantages of epoxy Novolacs include superior bonding characteristics. Epoxy Novolacs have an excellent bond strength. That means the material will cling tightly to the other surface layer of the substrate it is applied to, making it less likely to chip off or wear away. Not only does this ensure long-lasting performance, but it also means a thinner coat of epoxy Novolac will be just as or even more effective than thicker applications. Better chemical resistance. Epoxy Novolacs do not react with chemicals, both resisting damage and reducing the risk of chemical degradation and contamination. The resistance applies to both oxidizing and non-oxidizing acids. Increased heat resistance. Epoxy Novolac have a more cross-linked polymer than most other epoxy compounds, this increasing their thermal resistance, though it might also result in higher curing temperature for some compounds. Cost saving. Epoxy Novolacs have a higher initial price tag than many other epoxides, but their long-lasting attributes and unique strengths makes them a cost-effective option. Thanks for your attention. I hope you enjoy. Please share your thoughts, comments, or questions, and I will come back to you soon. Thank you.